going to grab a graph of a sine function. And we want to know, to start, does this is my graph of y equals sine x, and we're in section 4.7. Does this graph, would this function, the way I've graphed it, would this have an inverse? So I have this graph of y equals sine x. Would that function have an inverse? When we have a graph of a function, how do we tell? We have a nice test that we can use. You remember? Horizontal line test. Would this thing pass the horizontal line test? No. So this function would not have an inverse. Well, we want to be able to have an inverse function for the sine function. We want to be able to work with an inverse function. So the way we've graphed it does not have an inverse function. So what we're going to do so we can have an inverse function is I'm going to look at the graph just from negative pi over 2, pi over 2. I'm only going to look at that portion of the graph. And I'm going to just get rid of the rest of it. In this piece of the graph, y equals sine x takes on all its values. It goes from negative 1 to positive 1. That's sine of a number is always between negative 1 and positive 1. So my sine function takes on all its values. So we're not missing anything if we cut these other pieces off. We're just getting repeats of those same values. So we restrict the domain of our sine function to negative pi over 2 to pi over 2 to define our inverse. We're going to restrict our domain to negative pi over 2 to pi over 2. And just this red portion, this highlighted portion of the graph, that would pass the horizontal line test. So we would have an inverse. So we do that to define our inverse function, y equals inverse sine of x. So now we can define an inverse function just on that piece. And our graph of the inverse sine of x reflects over the line y equals x. So let me grab a picture of that. So there's our graph of y equals inverse sine of x. Make that a little smaller. So we restricted our domain. Now our range of our inverse function is negative pi over 2 to pi over 2. The inverse functions switch around the domain and the range. And the way we can think of the inverse sine function, for the regular sine function we plug in an angle and we get out a number. For the inverse sine function we plug in a number and we get out an angle. Inverse sine function gives us an angle. We can think of y equals inverse sine of x as the angle whose sine is x. So when we're trying to find the inverse sine of a number, we want an angle whose sine is x. And our angle has to be between negative pi over 2 and pi over 2. So what that means is we're looking at this half of my unit circle. My angles are only going to come from that half of the unit circle. And these angles below the x-axis here, we're calling negative. That's where the negative pi over 2 comes from. Negative pi over 2 to positive pi over 2. So let's look at a couple of examples to help us think about this. So the idea here is we restrict our domain so we can find an inverse function. Restrict the domain of y equals sine x. And our answer, what we get out of the inverse sine function, is an angle between negative pi over 2 and pi over 2. All right, so we want the inverse sine of negative 1. So what this is asking us is angle whose sine is negative 1. So what angle between negative pi over 2 and pi over 2 gives us a sine of negative 1? Sine is our y coordinate. Our y coordinate is negative 1, so we're straight down. So what angle is that? Down here? And we're between our inverse trig functions, we're always using radians. And we're between negative pi over 2 and pi over 2. So what would that angle be down here? We're thinking between negative pi over 2 and pi over 2. Negative pi over 2. And that is because the sine of negative pi over 2 equals negative 1. So we're looking for the angle whose sine is negative 1. Let's look at another one. The other way you'll see this written is arc sine. Arc sine and inverse sine are the same thing. 1/2. So this is asking what angle whose sine is 1/2. So what angle between negative pi over 2 and pi over 2 gives us a sine of 1/2? 1/2 is the small side of our 30, 60, 90 triangle. So what angle gives us a sine of 1/2? What is it? Pi over 4 is square root of 2 over 2. 1/2. What angle gives us the y coordinate of 1/2? Small side of our right triangle. There's my 1/2 there. So what angle is that? Pi over 6. Because the sine of pi over 6 equals 1/2. With these inverse functions, knowing your unit circle is going to be essential. This is the kind of thing that we're going to be looking at. Yes? No, once we have our memorization test, then I'm expecting that everybody's memorized the unit circle. Let's look at another one. How about the inverse sine of 3? What angle gives me a sine of 3? Let's look at this graph up here. What's the maximum of my sine graph? 1. The minimum is negative 1. What angle gives me a sine of 3? None. Does not exist. No angle has a sine bigger than 3. Sine has to, our angle, the number that we plug into the inverse sine function has to be between negative 1 and 1, because no angle has a sine bigger than 1 or smaller than negative. All right. We'll do a couple more examples like this. This is what your homework is like tonight. Finding the inverse sine of negative 1. Find the inverse sine of 1/2. Unit circle problems. We're going to do the same similar thing with cosine and tangent to define an inverse function for cosine and tangent. So let's look at a picture of our tangent or our cosine graph. So for cosine, y equals cosine x. This is not going to pass our horizontal line test. For the cosine, we're going to restrict the domain of our function from 0 to pi. So just this highlighted portion of my graph, that will pass the horizontal line test. It goes between positive 1 and negative 1, so it takes on all the possible values of our cosine function. So we're not losing anything by cutting the rest of this off. We're just losing repeats of those values. And then we get y equals, we can define y equals inverse cosine of x. And this is the angle whose cosine is x. And the angle has to be between 0 and pi. So for the inverse cosine function, we're only looking for our angles up here in the top half of the unit circle. And that's our graph of our function. Our inverse function is going to reflect over the line y equals x. Let me grab a picture of that. There's my graph of my inverse cosine function. I get an angle between 1 and between 0 and pi, between 0 and pi. So my angle between 0 and pi. So our inverse trig functions are always angles. What we get out of an inverse trig function is an angle. And we're going to do the same thing for tangent x. Questions before we go on? So what I want to do is talk about our restriction for tangent, and then we'll do some more. Then we'll kind of bring everything together, and then we'll do some more examples. All right, so for our tangent function, here is our graph of the tangent function. This is not going to pass the horizontal line test. So for the tangent function, we restrict our domain to between these two asymptotes, between negative pi over 2 and pi over 2. Our tangent function takes on all its values between negative infinity, down here close to this asymptote, to positive infinity there. So we're not leaving anything out by getting rid of the rest of those. And then we get y equals the inverse tangent of x. And this is the angle whose tangent is x. Our inverse trig functions are always angles. I'll grab a picture of our inverse tangent function, reflect over the line y equals x, and I get this function kind of laying sideways here. So our angle is between negative pi over 2 and pi over 2. And for the inverse tangent function, I can plug in any number. So our inverse functions switch our domain and range. So again, for the inverse tangent function, when we're looking for this angle, we're looking in this half of the unit circle, and our angles below the positive x-axis, we're saying are negative. All right, questions about our domain restrictions. The reason we restrict the domains of our original function is so that we can define an inverse function. We want to be able to work with inverse functions. All right, so let's bring all this information kind of together in one place. And then we'll do some more examples. So for our inverse functions, y equals the inverse sine of x. If and only if sine of y equals x. The domain of the inverse tangent function, or sorry, inverse sine function, the numbers that we're allowed to plug in, -1 to 1, because no angle has a sign bigger than 1 or smaller than -1. And our range, our angles that we get out, are between negative pi over 2 and pi over 2. Y equals inverse cosine of x. If and only if cosine y equals x. Y is an angle. Our domain for our inverse cosine function, -1 to 1. No angle has a cosine that's bigger than 1 or smaller than -1. And our range for the inverse cosine function is 0 to pi, because that's where we restricted the range, the domain of our original function. So our angle that we get from the inverse cosine function has to be between 0 and pi. And y equals inverse tangent x if and only if tangent y equals x. And our domain for the inverse tangent function, we can plug any number into the inverse tangent function, because the range of the tangent function is -infinity to infinity. The domain of our inverse function becomes -infinity to infinity, and the range is minus pi over 2 to pi over 2. So the angle that we get out of the inverse tangent function has to be between negative pi over 2 and pi over 2. Yes?
So is the domain of the inverse always
the range?
Or the range of the
Yes. So inverse functions switch the domains and the ranges.
Okay.
And when we're working with inverse functions, our inverse trig functions, always in radians. All right, so let's look at some more examples, thinking along these lines. All of our homework assignments, all the problems have to do with thinking about the inverse trig functions, that they're angles, and our domain restrictions of our original function. So let's find the inverse cosine of square root of 3 over 2. So this is asking us what angle between 0 and pi has a cosine of square root of 3 over 2. Cosine is our x-coordinate. So our x-coordinate is the long side of our 30, 60, 90 triangle. So what angle gives us the long side on the x-axis of square root of 3 over 2? pi over 6. And this is because the cosine of pi over 6 is the square root of 3 over 2. How about the tangent, inverse tangent of 1? What angle between negative pi over 2 and pi over 2 gives us a tangent of 1? To get a tangent of 1, the sine and the cosine have to be the same. So what's that one going to be? Pi over 4. So with these inverse functions, we're working kind of both ways with our unit circle. We have to know what our sines and cosines are. We have to know what our angles correspond to various sines and cosines. We have to think about our unit circle going both directions. How about the arc cosine of negative 0.5? Arc cosine is the same thing as the inverse cosine. So this is saying negative 1/2. So what angle between 0 and pi has a cosine of negative 1/2? So the x coordinate is negative 1/2. The x coordinate is the short side of my special right triangle. It's going to be 2 pi over 3. And this is because the cosine of 2 pi over 3 equals negative 1/2. These two are saying the same thing. How about our tangent of square root of 3 over 3? So what angle between negative pi over 2 and pi over 2 has a tangent of square root of 3 over 3? So we can narrow this down a little bit. For the inverse tangent, we're looking over here on this half of the unit circle. The tangent positive, so what quadrant does it have to be in? First. So we've narrowed it down. We're up here. And now there are only two possibilities. What are the two angles in the first quadrant that have a square root of 3 involved for our sine or cosine? Pi over 6 or pi over 3. So we just have to decide which one is going to give us a tangent of square root of 3 over 3. If we're not sure, let's pick one and let's figure it out. So what do we want to try? Pi over 3. Pi over 3. The sine, what are the coordinates on our unit circle at pi over 3? Pi over 3. The y coordinate is the long one. The x coordinate is the short one. 1/2. Square root of 3 over 2. The tangent, pi over 3, 1/2, divided by the, did I do that right? Tangent. Yeah. So my tangent is going to be 1/2 times 2 over square root of 3. I get square root 1 over square root of 3, which is square root of 3 over 3. Yes? Did I do this upside down? Thank you. I did cotangent. All right, so these are the kinds of things that we need to remember when we're working these problems. What is sine? What is cosine? What's our x coordinate? What's our y coordinate? So tangent is y over x, square root of 3 over 2, divided by 1/2. I'm glad somebody caught that. So this gives me square root of 3 over 2 times 2 over 1, and I just get square root of 3. So the tangent of pi over 3 is square root of 3. So what does that leave? That has to be our answer. Pi over 6. All right, so when we're working with these, all the problems tonight are asking us to think of this relationship, and this tells me that the tangent of pi over 6 is the square root of 3 over 3. These two mean the same thing. So the homework tonight is working with these relationships. There are a couple of problems that ask you to find an inverse sine, an inverse cosine, or an inverse tangent using your calculator. Make sure your calculator is in radian mode, and then you can use your inverse cosine, inverse sine, or inverse tangent button to evaluate that in your calculator. Anytime that the problem says without using a calculator or an exact answer, something like that, that tells you you're going to be using the unit circle. All right. All right, there you go.